We've spent some time talking about confidence intervals, and now we're going to switch gears and we're going to talk about hypothesis tests. So those are the two big ideas in inferential statistics, are confidence intervals and hypothesis tests. And as a motivating example, let's think about the idea of ESP. So there are people who believe that extrasensory perception exists. So basically, people can read minds or talk without speaking and communicate in that way. And it's not clear whether ESP does or doesn't exist. So there's this test for ESP that uses Zener cards, and I pulled this picture off of Wikipedia. There are 5 cards, and they have these different symbols on them. And the way that the Zener card test works is you have one person who's looking at a card, and then on the other side of a wall or something is a person who might have ESP, and they try to read the mind of the person looking at the card and figure out which one they're looking at. So because there are 5 cards, we could go back to our knowledge of probability and we could say, if you were just guessing at random, you'd probably get the card right 1 out of 5 times. That's 20% of the time. Just at random, you might say, you're looking at the circle, and you'd be right. But if someone really had ESP, they should be able to guess the correct card more than 20% of the time. And the question is, how much more often would they need to get it right for us to believe the ESP exists? So one way to determine if something like that is true or not is to use a statistical test. And a statistical test is a procedure that we're going to run through where we're going to determine if the results from our little sample are convincing enough for us to conclude something about the whole population. So that's statistical inference, drawing a conclusion from the sample about the population. And when we do a statistical test, we need to set out hypotheses. So hypotheses are like guesses, but in statistics, we have a very formal way of writing out our hypotheses. And there's always 2. There's the null hypothesis, and we denote that as H0 or H0. And that's a statement about there being no effect, no difference, nothing going on. We also have the alternative hypothesis, HA, and that's the thing that would be really interesting if it was true. We're sort of secretly hoping to be able to say that the alternative hypothesis is the thing because the null is there being no effect, no difference, nothing going on. It would be interesting if there turned out to be something going on. So with the ESP example, we could either use words or parameters to write out our hypotheses. And with words, we would say our null hypothesis, the kind of boring thing, that there's no effect, that would be that ESP does not exist. And the alternative hypothesis would be that ESP does exist. That's the interesting thing that we're kind of secretly hoping is true. But most of the time, we write out our hypotheses in terms of parameters. So in this case, our parameter is a proportion, p, and our null hypothesis is that p is less than or equal to 1/5. So truly, this person is only getting it right 1/5 of the time, or maybe even less than 1/5 of the time. And the alternative hypothesis is that the true proportion is greater than 1/5, that the person is actually truly getting it right more than 20% of the time. So here are some facts or tips about hypotheses. One is that hypotheses are always written about the population parameter, so about mu or p or mu1 minus mu2 or p1 minus p2, and they're never about the sample statistics. So those are our x bars and p hats. The null hypothesis, that's the boring thing. We're trying to gather evidence against the null hypothesis. And the alternative hypothesis is the exciting thing that would maybe make a headline. I also like the hypotheses to cover the entire possibility space. So if there's an inequality in one hypothesis, I like to have the complementary version in the other. And this is comple with the LE, not like a compliment, something nice that someone says, complement the other half. So in this case, we had our null hypothesis was that P is less than or equal to 1/5, and our alternative was that P is greater than 1/5, and that covers the entire possibility space. P could be less than 1/5, it could be equal to 1/5, or it could be greater than 1/5, and we're covering all the possibilities there. I'll say that the textbook doesn't always do it this way. So in the textbook, the null hypothesis is usually with an equal sign. So it would say P equal to 1/5, and then the alternative would be something like P greater than 1/5. So over here, this is what Dr. M prefers, and over on the other side, that's what the textbook does. So if you are writing something for an exam, I'd like to see it this way, where it covers the entire space. If you're doing the homework or you're looking at the book, the null hypothesis is always going to have an equal sign in it. So I apologize for that inconsistency, but that's the way I like to do it. The inequality that's going to be in the alternative, that's going to come from the question of interest. So in the case of ESP, we want to know, is it truly more than 1/5? So that's what we would put in our alternative hypothesis. I'm just going to draw you my favorite picture again. Of course, we've got our big oval. This is the population. So that's all the people or cells or trees, whatever it is that we're studying. And then we're going to have the smaller version, and that's our sample. And there is a procedure where we're going to pull from the population to form the sample. This is sampling that goes in that direction. And then the point of statistics is to do inference, drawing conclusions about the population based only on information from the sample. So in this case, we had some type of p hat, and we'd like to draw a conclusion about a p. And the big question that we're asking when we do hypothesis testing is this number different than 0? So remember, the big question with confidence intervals was, what other reasonable values could I have observed? And for hypothesis tests, it's, is this number different than 0? Maybe I'll write 0 out as a word. This is number different than 0. So let's think about another example. This is an example from this German shoe brand, and the name of the brand is Atheist. And they noticed that their packages were taking a long time to arrive in the United States. So they ran this experiment. They often are putting this Atheist branded tape on the outside of their box. So they're taping the box closed with their brand name, which is the word Atheist. They suspected that maybe it was that tape that was making the packages arrive more slowly. So they ran an experiment. It says they sent 178 packages to 89 people, and each person was sent 2 packages. One was sealed with Atheist branded packing tape, and the other with neutral tape. So just like plain brown or clear tape. And then they mailed them all the same day. So let's just kind of summarize that. 178 packages, 2 each to 89 people, one with the branded tape and the other with the plain tape, and then they're tracking how many days each package took to be delivered. So we're going to need to think about our explanatory and response variables here. So this is going back a little ways. Our response variable is the thing that we think might be responding. So I usually start with that one. So the response here is the days to arrival. And then the explanatory variable is the type of tape. And our question is the time to arrival impacted by the type of tape? That's our kind of big question that we're trying to answer using a statistical test. And then we could think about the hypotheses. So let's use mu sub b to mean the average number of days that it takes for the package to be delivered using the branded tape, and mu sub p to be the average number of days that it takes to arrive using plain tape. And we could write our hypotheses out a few different ways. So one would be with words. The null hypothesis, there's no difference in average time to arrival depending on the tape used. And the alternative hypothesis, there is a difference in average time depending on the tape. We could also write it out using parameters. So we could say mu sub b equal to mu sub p. That would be the boring thing. And then the alternative, which covers the rest of the possibility space, mu sub b is not equal to mu sub p. Or we could equivalently write these same hypotheses about the parameters like this down here by just subtracting mu sub p from both sides. And then we'd have mu sub b minus mu sub p is equal to 0. And the alternative, mu sub b minus mu sub p, is not equal to 0. And so this allows me to phrase it in the way where we could say, is this number different than 0? So we would have some x bar sub b minus x bar sub p, and that number wouldn't be 0. And we'd like to know, is that in the population, is it truly different than 0? So that's what these hypotheses allow us to ask. So the goal of the hypothesis test is to gather evidence, and then we're going to determine if we have enough evidence to reject the null hypothesis in favor of the alternative. And we're asking that sort of big question, is this number different from 0? So we could think about this with the ESP question. We have our null hypothesis that the true proportion is less than or equal to 1/5. The alternative is the true proportion is greater than 1/5. And then we'd have some observed data, some p hat. And the question is, how much evidence would you personally need in order to think that the true p was greater than 1/5? So would you need to see, 1 out of 6 getting it right? 1 out of 5 would convince you, 1 out of 4, etc. And we'll talk about this in synchronous class to see what people's opinions are. There's no right answer here. It's just kind of what your feeling is about there being enough evidence. And we could ask the same question with the atheist shoes. How much evidence would we need to determine that there was a difference in average time? If it was a day different, would that be enough evidence? Or 3 days different? Or 10 days different? Or 100 days different? How big of a difference would it need to be for us to say that there was really a difference? Again, I'm just asking you an opinion question. And then as we go forward through this chapter, we're going to get more statistical. We're going to learn how to statistically measure the strength of the evidence against the null hypothesis. But that'll come later.